In 1989, the world was poised for a revolution. Two electrochemists, Martin Fleischmann and Stanley Pons, made an extraordinary announcement. They had discovered a form of cold fusion, a process that could generate vast amounts of clean energy at room temperature. This was nothing short of groundbreaking, a potential solution to the world's growing energy needs, free from pollution, and, most importantly, safe. The claim was made with high expectations. Cold fusion, if real, promised virtually unlimited energy. Imagine powering entire cities with just a small amount of hydrogen, without the risks of nuclear meltdowns or hazardous waste. The idea was tantalizing. Fleischmann and Pons believed they had achieved this miracle using a simple tabletop experiment involving palladium electrodes, heavy water, and an electric current. The scientific community, governments, and media were captivated. The race for a new energy era had seemingly begun. But as the excitement grew, so did the scrutiny. The key to science is reproducibility. And soon, other laboratories around the world began trying to replicate Fleischmann and Pons' results. But things didn't go as planned. One by one, teams of scientists, eager to verify this groundbreaking claim, failed to reproduce the excess heat that was central to the cold fusion promise. This led to questions. Were the initial results a fluke? A mistake? Or something even worse? The skepticism intensified. The scientific establishment, which had been cautiously optimistic at first, began to distance itself from the project. Major research centers, once enthusiastic, closed their cold fusion programs. Critics argued that Fleischmann and Pons had rushed their announcement, bypassing the peer review process that ensures scientific rigor. There were also accusations of improper methodology. Had the data been misinterpreted, or were there experimental errors? Fleischmann and Pons had claimed to observe small, but significant amounts of excess heat, but no harmful radiation, a signature of conventional nuclear fusion. This discrepancy raised doubts. After all, how could nuclear fusion occur without producing the harmful byproducts we expect? Months passed, and the world's initial excitement turned into disappointment. By the end of 1989, most scientists had abandoned the idea of cold fusion. It became known as a scientific embarrassment, a cautionary tale of rushing to claim victory without enough evidence. But the story doesn't end there. What if the initial promise wasn't wrong, but just misunderstood? A few dedicated researchers have continued to study cold fusion, or what is now called low-energy nuclear reactions, or LENR. The field is far from dead. While mainstream science remains skeptical, small breakthroughs have been claimed over the years, though none with the certainty needed to overturn the conclusions of 1989. And here's an interesting anecdote. In 1992, just 3 years after the public fallout, Fleischmann and Pons quietly moved their research to France, funded by a Japanese company still interested in the potential of cold fusion. The work continued, largely in secret, for several years. While nothing groundbreaking came from it, it showed the persistent allure of their discovery. So what do we take away from this story? Cold fusion, whether a fleeting scientific error or an unrealized breakthrough, teaches us an important lesson about the nature of scientific discovery. Sometimes, the path to truth is paved with wrong turns, dead ends, and setbacks. But without the willingness to explore the unknown, we might never make progress at all. The question remains, will cold fusion ever rise again from the ashes of controversy? Only time will tell.